All right, so welcome back, everybody. Today as I mentioned in Campus Wire, we're gonna do it over Zoom because I'm still not 100% sure that I don't carry COVID if I have COVID. But thanks everybody for asking. Sending notes and this stuff. Uh, I'm feeling much more better. Uh, so there's a question in the chat about, do we need to submit our code / working directory for our own project? Yeah, so what I posted during the weekend, if you check out Campus Wire, was that I'm expecting you to, whatever code you have, you just upload it on GitHub and just send me the link to your repo. So that's the easiest thing to do for your project. Do read the post that I did on Campus Wire. I just break down for each project what you should do, what are you expect, what are the expectations, and so on. Check that out, and then either post your question there directly, or ask me, email me, or DM me, or we can talk during the lecture next time about these things about your project. All right. So for your original project, if you have done something, so my suggestion to you is probably it would be better to share your code with us as well. So you have to do your video and a short write-up. So I think the easiest thing to do is just upload your code in GitHub and send me the link to it. Any other questions? Okay, so today I want to talk about CPS security. Talk about different things in CPS. What is CPS and what is security? This would be probably a shorter lecture. So if you have more time, I'm going to switch to lecture 17, which is hardware security as well. So we're going to talk about that as well, which is going to be kind of like the last topic that we're going to discuss in this course. A few logistics. So as I mentioned, I posted a few different posts on Campus Wire. Give me a second, I'll be right back. Okay. Right, sorry about that. So as I said, a few posts I put on Campus Wire, probably most of you have read. The first thing is your quiz this weekend. So probably we're gonna do it the same way that we did last time. We'll release it on midnight of Friday. And you will have 2 days until I think Saturday night to finish the quiz. The format would be very similar to quiz 1, and the topics would be everything after quiz 1. All right, after quiz 1, everything including the lecture today, but not the lecture on Wednesday. All right, so that would be the concepts that we're gonna cover in quiz 2. The second thing you need to pay attention to is this sign-up sheet, this Google form that I posted on Campus Wire. Please go there and fill in that sign-up sheet. So it's just basically just indicating whether you're going to take the final exam or whether you're going to do the final project. And there's some tiny questions that you need to answer for each of them as well. For those of you who wants to do the final exam, first of all, I need to know how many of you are going to do that. And then, as I said before, the final exam would be including everything that we discuss in this course. Format though will be similar to quiz 1 and 2, probably slightly shorter than the other two in terms of number of questions. All right. And I also posted a clarification on final project for each type of project, what you need to do. And I'm going to share a folder with you so that you can upload your stuff there. So I'm going to post that folder either today or sometime this week. All right. So these three things, important things. Any questions? Is everything clear? Okay. And then grades for quiz 1 hopefully will be released soon before Friday. I'll try my best to release your grades before Friday as well. All right. Okay. And before we also talk about cyber-physical systems, which is actually kind of relevant to the discussion that we had, I also posted another post about the disturbing news of Russia-Ukraine conflict and the war. And what you can see is the impact of cyber attacks these days in our modern lives, malwares and denial of service attacks. We already discussed this a little bit. Maybe next week, if you have time, I'll talk a little bit more about malwares and what malware is, what are the different types of malware and so on. So you give you a little bit of more information there. But it's, I think, one of those, I mean, we have always seen cyber attacks at the state level. So countries attacking each other. Stuxnet, for example, was one. Attacks to Ukraine, actually, infrastructure by Russia a few years back was another big example. But I think this was the first time there's actually, the actual physical wars happened at the same time with, cyber attacks. So you can see cyber attacks is another type of weapon that can be used in modern wars, which is kind of disturbing, but also shows you why cyber attacks becoming more and more important. But now let's actually talk about cyber physical systems in general, all right? What cyber physical system is basically, a plethora of IoT, CPS, embedded system, PLC, sensing, and stuff like that. There are different naming conventions. They're slightly different from each other, but generally they're all referring to kind of same sort of system, where essentially what we have is some sort of, sensing ability. The sensing usually goes into some sort of local processing. And this local processing either goes through some sort of actuation, or it goes through the network and goes to another device, typically a cloud device. And that cloud device actually leads back to the local process and then creates an actuation. So this could be either back and forth between the two, or this could be directly, impacting this. And this cyber physical systems, the reason is that basically we are interacting with the physical world through sensing and through actuation, all right? It could be either of these two, or it could be both of them at the same time. The Internet of Things is mainly focusing on the connection aspects of things, that the fact that, we have some sort of sensors, actuators, and local processing, and they are all connected to each other and connected to some cloud systems. The cyber physical ones is basically more focusing on the sensing and actuation part. And the embedded systems is basically kind of focusing on the systems parts of the things. But in reality, really, the three terms are almost similar these days. So there is no significant difference between what is called a cyber physical, what is called an IoT, or what is an embedded systems. Really, they are almost the same thing. And then there's also, programmable logic controllers, PLCs. These are kind of similar to embedded systems, but slightly different in terms of structure. So these are mainly used much more simpler in terms of, programming model and programming capabilities, and in terms of capabilities in general, but they are actually used in more industrial settings because they're more robust. They usually use for doing some sort of actuation, like opening a valve, closing a valve, raising temperature, lowering temperature, opens specific I don't know, door or knob or things like that. All right, so this is typically what the PLC is going to be used for. And there is, of course, the circuit design part of the things, and there is the sensing and actuation part of the things as well. The whole area of this, the whole design of this is actually a large area. There are various things people are working on the sensing part, on designing low power systems for local processing, tiny machine learning. These are all within the systems. Of course, the networking part is a huge part as well. Wireless sensing, wireless sensors is a large area of research. And of course, the communication and the cloud versus edge communication is another interesting area of research. And finally, new ways of actuation is another area of research. So these are the general non-security part of it. But what we want to talk about today is, in this ecosystem, what is the challenges in terms of security and privacy, all right? But this is actually where I would say 80% of computer science and computer engineering really is these days. Most of the research going on around some aspects of this ecosystem. So that's why cyber physical systems are so important. Any questions at this point? So yeah, to just give you some applications, of course, the main things about cyber physical systems is that they are mainly used for more industrial type applications. So in an industry like factory lines, controlling of the pipeline. Oil and gas companies usually use lots of PLCs for their systems. Various kind of manufacturing robots is one other key examples of cyber physical systems. Then there's whole bunch of notion of smart homes and smart cities. This is actually an up and coming concepts in computer engineering. Connecting seemingly passive devices such as your coffee machine, your toaster, and stuff like that, and then all of a sudden make them smart so that you can control them and do the various things with it. There's huge benefit in using medical devices and using embedded systems in medical domains. So ML generally is a term that's being used in mobile health is also really growing area of research. In autonomous systems is also, there's lots of research. So autonomous car, obviously, most of you are already familiar with it. Cyber physical systems play a key role there. Drones and autonomous robots is also another class of devices, such as the starships that we have on campus. That's another examples of the systems. And then smart agriculture. And if I want to add more, there's probably satellites and space applications is another key examples of this main CPS application. So as I said, this is like a growing area of research, and we are actually experiencing what's called Industry 4.0. So the first revolution, industrial revolution, is when we actually managed to have motors in some sense, water power, steam power, and so on. Then the electricity was kind of like where the second industrial revolution came in, and assembly lines, and we managed to build systems. The automation was what's called the third industrial revolutions. We managed to use robotics and so on. And what we are experiencing right now is actually the fourth industrial revolution in the entire history of humankind. And that's because of the cyber physical system. So that's why this is an important area of research. Any questions so far about the generic things about cyber physical systems? Okay, so now let's actually get into a little bit of more security. That's what's relevant to this course. So of course, the biggest thing is in industrial CPS, there are various things that can be attacked in defense. This picture that I'm showing here is actually a nice one. That's kind of like, show almost everything that can happen. So of course we have, sensors and robots as the like, the lowest end of this chain, and the highest end is basically the other end is basically the cloud and gateway and distributed systems. There are various attacks that can happen in various points of this this large system. There could be malware analysis, there could be ransomware, there could be denial of service attacks or distributed denial of service attacks. There could be phishing attacks, there could be vulnerabilities, and there could be device hacking. All right, device hacking and vulnerabilities, these are basically the two things that extensively discussed in this course. Hacking, mainly when we are saying hacking in this concept, is means using some sort of usually a memory vulnerability in order to do the control flow hijacking. So remember when we talked about stack buffer overflow or ROPs and these type of attacks, is basically where you initially use some vulnerability in the system in order to launch those attacks. So that's what we mainly meant by device hacking. The vulnerabilities could be, again, essentially all of these things can be a vulnerability, but mainly vulnerabilities is when either the system has some sort of a bug that doesn't do what it's supposed to, or when we are having something like a side channel attacks where because of the implementation, the system can leak some information. So we can have, for example, vulnerabilities. If you follow these keys, you'll see that, for example, there are these vulnerabilities at the different points. So there could be vulnerability on the robotic side, the firmware of the robot, or on the switch, or even on the gateway, and even on the SCADA, the control systems of the entire, entire cyber physical system. So there could be vulnerabilities in all of these systems, because essentially at the end of the day, these are different pieces of software that there could be bugs in them, or the adversary can attack them in various ways. About malware, ransomware, denial of service, and phishing, we're going to talk a little bit about them next week. What they are, what's the difference, for example, what's the difference between malware and ransomware. This is not the terminology that I typically use, so I usually put ransomware inside the malware as well. I'm going to talk about next week. But generally, the idea here, most of these things are, the idea here is that using this vulnerabilities here, or hacking here, the adversary managed to do something malicious and do something harmful to the systems. For example, the robot does not work properly as expected. The information is being sent out to wrong, gateways. Information actually being maybe leaked out in other cases. SCADA systems doesn't work properly. So for example, the valves and switches does not work. And at the end of the day, the goal here is to disrupt this normal behavior of the system, right? So for example, just imagine this is a manufacturing company using any of these, different types of attacks, malware, whether it be malware or vulnerabilities of side channels. The idea is either disrupt this or, leak some information to the outside world, right? So that's usually the idea of the war that we have in cyber physical systems. Any questions about this picture? And then another example is, smart homes and smart cities. So, we have things like, smart videos and smart TVs. We have different consoles. We have, interactive devices, voice control devices. We have smart, smart bulbs or smart refrigerator and things like that. We have drones and we have, robotic arms. We have, autonomous cars and autonomous systems. We have human-like robots. So these are all different examples. And now in terms of security, you can think about every single one of these becomes an active computer. And the same way that we showed so far in this course, at various points we can attack the system, we can basically attack all these different devices. So far, what we have discussed, we are always thinking about the victim as this process or this computer that's kind of like, it doesn't have any actuation, it doesn't have any sensing, right? It's just something that sits passively. So all we kind of could have, captured from that was either disrupting the service or stealing some information, right? But now when we are moving to the cyber physical domain, now all of a sudden we can actually change that into actions and sensing values, right? So if we manage to attack, for example, this car, we don't need to steal information, but we can actually, for example, force this car to bump into another car, right? Or for example, if we manage to attack a smart home, maybe we can attack the smart lock, so we can open the door and then go inside and I don't know, steal some other valuables, right? So the idea of cyber physical system and what is make it more different than what we have discussed so far is that interestingly, all of a sudden, things that they kind of like showed in the past few weeks now kind of makes sense because we can now actually use this and put this in action in terms of adversary war. All right. So that's where we are in terms of why cyber physical systems are important. So as I said, typically a CPS structure has some sensing capabilities, some processing. It could be going to the network and to the cloud and then actuation, or sometimes it's just the loop will be closed locally. So it's sensing, processing, and actuation. It doesn't have to communicate to any other systems. All right. So in this realm, let's think about what is the threat model and what are the attack vectors. What can we do to attack the system? And we're going to go through each one of these one by one and talk about the attack vectors and potential defenses. Right? But before I actually I mean, of course, the answer to this, that what are the attack vectors? Unfortunately, the answer is all of them are potentially hackable and attackable, as we extensively talk about, the various different area of this in this course and during campus where we talked about, what is attackable, and we always said that everything is attackable. So let's actually go through these one by one. So for sensor security, there are three main things that we can think of that can potentially be important. One is for sensor security, the attacker. What the attacker can do is that changing the physical domain, what can be sensed, right? And interestingly, this is actually what we have seen before in this course as well. Where we've seen it very early on when we were talking about evasion attacks and physical machine learning attacks. Remember when we said, for example, there is an image and all of a sudden we added this patch to this image, right? Or we created this adversarial samples in order to fool our systems. Essentially, when we did that, what we were doing was attacking a cyber physical system in some sense, where part of it was the machine learning part, which machine learning part it basically was this local processing part, but that machine learning was part of the bigger system, which was the cyber physical systems. Whereas, for example, it could have been a car with the camera on it, and then receiving some images, do some processing, and then change the direction of the car, or accelerating or braking the car, right? So that was our actuation. So what happens is that the adversary can actively change the scene, adding the patch, moving things around, making sure that the sensor is making a wrong decision is what the attacker can do. And in terms of defense, is actually the defense also needs to do the same thing. So basically, the defense also needs to make sure that the environment is trustworthy. So there should be some notion of verifying the environment, or at least testing the environment in order to make sure that the system is trustworthy, right? So that's number one. The second thing is the attacker does not need to change the environment, but it can interfere with the environment and the sensor. What does that mean? It means, for example, I mean, there are some, if you're looking into your paper listings, you will see things like, dolphin attacks, where the idea is that we had this, voice command system, something like an Amazon Alexa, which, listen to some voice. And what we can do is that instead of sending the actual voice in the range of, a human voice frequency, the people have shown that if you send like a high frequency or maybe even a very low frequency, the system still can hear this and make some action based off that. And the importance of this is that this is not an audible signal. So an attacker can very stealthy attack the system, send this non-audible signals to your voice command system, such as your Alexa, and do what he or she wants to do. For example, let's say your Amazon Alexa is able to lock or unlock your door. What the attacker can do is maybe sending this inaudible signal to your system when he or she is nearby, and then without you actually even knowing that Amazon Alexa has unlocked your system or your door, that the door gets unlocked, right? So this is basically in some senses changing the physical world, but it's more of like an interference. So there's this primary channel, which in this case, for example, is the human voice, but there's this additional channel that's kind of interfering with the sensor, and that can create lots of issues. Again, on the defense side, the idea is again trying to protect the system against this type of interference, right? So either make the sensor robust against this sort of interference, or using additional mechanisms to make sure that this sensing values can be trusted. For example, maybe using other modalities, or using multiple sensors, or using nearby devices. These are various things that the defense system can do in order to improve the security of the system. All right. Any question here? So that's with the interference. And the third thing is the faults. We also, like last week, I think we talked about faults more extensively when we were talking about physical attacks. This can actually happen on the sensor side as well. So remember, for example, we said that if we do undervolting, change the voltage, we can create faults. Here we can do that. We can do more things as well. For example, people have shown that if they shine a laser on a specific device, they can actually flip some values in that device while the device is, for example, sensing specific values. And this could result in some attacks. It could be an integrity attack, or it could be a confidentiality attack. So this kind of adding additional faults can be another way of attacking the systems. All of these three is kind of very similar in the ideas. In other words, we are trying to see what the sensor can receive and change that. So basically, if this is our sensor, this is the physical world here, and this is the digital world here, the attacker tries to change things here. All right, so the attacker tries to change things here, either by adding patches, by creating interference, or by creating faults. One of these three ways the attacker managed to change things, and then this will be translated into incorrect values in the digital world, and the rest of it is just basically the attacker planted this adversarial sample and then fool the systems in various ways, depending on what the goal of the attacker is. All right. One important thing to note here is that this sensing modalities is actually an active area of research. So there is, it's not just vision or voice or acoustic or temperature. There's things like, high frequency sensing. There is LiDAR sensing, there is, activity sensing. There are various ways of sensing, and this itself, that coming up with new modalities, more effective modalities, is actually what we are actively doing research as well. So as we added more and more of these, sensing modalities, basically there are lots of new opportunities, unfortunately, for the attackers. But on the plus side, there's actually also more opportunities for the defenders. So for example, maybe we can use a terahertz, sensor to make sure that there's no interference in our systems, right? So there are various ways that you can think about this. And this is actually quite exciting and interesting area of research, the sensor security, both in the attack terms and both in the defense. All right, any questions here? The second thing is the local process, right? So now we sense the values has been converted from the analog domain to the digital domain. Now we are, getting some digital values, and we need to process this into our like main system. This could be an ML system, it could be a signal processing system, it could be a regular CPU, it could be anything else, right? So this is typically what we do in our local process, right? One important thing to note here is that what can be attacked and what is the attack vector and threat model, it really depends on the class of devices. And as I said, since we are kind of like, looking at the different range of systems, we need to also be careful of what we can expect, right? So we have IoTs, we have embedded systems, we have medical devices, we have PLCs. Some of them, for example, have network communication. Some of them have more powerful processors. Some of them have less powerful processors, and so on and so forth, right? So what will happen is that when we're thinking about local process and compare it to, for example, what we have discussed so far in this class, is that generally we have heterogeneity in these systems, and we might have very low-end system devices. We might have very high-end devices in this combination, in this ecosystem. So we have to consider all of those things when we are talking about the security. But the threats that we talked about are mainly the same threats that we have talked before: memory bugs, software bugs. Network connectivity, always an issue. Side channels is always an issue. So things that, the ways that the attacker can attack the system is the same that we discussed. But the only thing is that, different class of devices might have different capabilities. Another large difference between what we have discussed so far and cyber physical systems is because of the user interaction. So typically it's very common that in a cyber physical system, there is some sort of interaction with that user. And this user can easily become an attacker, right? So the attacker can also interact freely and more easily with the device. And this can potentially create some more problems and threats, right? So, for example, remember we said that in a machine learning system, the attacker can, send queries, get information, and train some sort of like a shadow model. This is exactly where this idea can be realized, right? Where the attacker can, constantly interact with the device, get these values, and trains this, right? And this could be, applied to any other sort of attacks in the system. So if the user interaction is more freely available, then the potential for loading an attack would be also higher, right? So that's a big issue that we need to think about. All right. So that's one thing to notice. And of course, when we have user interaction, also the chances of doing things like buffer overflow also becomes higher, right? Because the attacker can send and receive various different inputs. So now, for example, if the attacker can manage to find vulnerabilities such as buffer overflow, they can send return addresses, they can overwrite the buffer, and so on and so forth, right? So this interaction potentially can cause lots of problems, but on the other hand, interaction is something that we do really want in CPS systems, right? There is a whole bunch of, area of research such as human computer HCI, which the whole idea is that how we can even improve or make this interaction much more richer. So interaction is not something that we can easily discard, but we have to be aware of it. And when we are building secure systems, we have to make sure that this interaction is secure. All right. And then another different thing is the malware part. So remember for example, when we talked about things like buffer overflow, we said that essentially the attack has two parts, right? The attack has this vulnerability part, which we kind of like, override the stack and jump to some part of the program, some other part of the program. And we said that this is basically the part that we kind of like, we call it payload, which is basically what's the malicious part of the program is, what's the malicious part of the attacker agenda is, right? And then we said, for example, this could be what's called a shell code, where the idea was that the attacker wants to open a shell, open the terminal, and then basically gets the full control of the system, right? And as I said, usually for a cloud system, that's the only thing that an attacker can do. But when we are moving to a system with an actuation and real sensing capabilities, then different payloads can be used, right? So I already discussed that. For example, if you attack an autonomous car, then you can create traffic or you can create accidents. That's very different than when you're attacking Amazon Web Services computers, which essentially is only information is there and you can only steal information, right? So the idea here is that payloads can be very different and there could be physical attacks in this scenario, right? Any questions at this point? All right. So just to give you some potential attacks, we already discussed it. Physical attacks is the main one, physical side channels attacks. And memory corruption and privacy attacks is another one. False attacks is always an issue that we need to care about. Digital side channels are not that important in this scenario because essentially we are talking about physical interaction with the systems and not running multiple processes. Another thing is that usually when we're talking about cyber physical systems, we're talking about low-end CPUs. And when we are talking about low-end CPUs, we mean mainly single core systems that doesn't support multi-tenancy and doesn't support, multiple applications at the same time. So things that we discussed, for example, about cache side channel attacks or Spectre and Meltdown and so on and so forth. These are only happens if you have multiple processes on the same system. So if you have only one process, there's no notion of, something like a cache side channel. So that's why digital side channels is less of a problem when you're doing the local processing, but physical side channels all of a sudden becomes even more important because now you have physical proximity, you have interaction and all those things. Another important things to remember is that one of the other key differences between when we are talking about attacks to local systems versus attacks to server systems is the battery and the energy. So one of the key goals of the attacker could be depleting the battery or increasing the energy consumption. Especially this is, for example, is very valid in medical devices, implants, right? So because when you implant something into someone's body, the whole operation is very costly. The device is very costly. So you definitely want to have the system as low power as possible. You want to reduce, you want to enhance the lifetime of the device and so on. So if there is an attack that reduce the lifetime of this device significantly, that itself is a very important attacks and very serious attacks, right? Same goes for system that operates on batteries. That, for example, let's say controls a specific valves in your large system. If you manage to deplete the battery of that, then you basically it's kind of like a denial of service attacks, right? We basically shut down the system, entire systems by depleting the battery. And if you remember, we always said that the goal of the adversary are these three things: confidentiality, integrity, and availability, right? So for example, if you deplete the battery, we might be able to actually leak some information, but in most cases, when we're depleting the battery, we are targeting the availability of the system, all right? But generally, what I want to say is the key takeaway from this is that, of course, we have all those attacks that we had before. In addition, we usually have this attacks on the battery of the systems, right? Any questions? Okay. So on the network side, so remember we said about sensing, then local processing, and then said here we basically have two options. Either we go directly to the actuation, so the whole thing becomes local, or we might usually use network and send it to some sort of nearby device or another cloud device and so on and so forth, so multiple hubs, and then eventually send the result back and then send it to the actuation, right? So either of these two. For network, of course, network security is a very established area of, area in security. In this course, we didn't really have time to go over network security as a module, mainly because, we wanted to focus more on algorithm side and processing side. but probably sometime maybe in future we need to add this module as well. So I mean, traditional network security is, I mean, regardless of edge devices, generally when we are communicating between two devices, we need to satisfy again the confidentiality, integrity, and availability of the system. The internet security, of course, is a big thing for itself. But what we need to think about in the realms of cyber physical systems, and what is distinguished us from regular computer security and network security, is these kind of bullet points that I'm showing here. One is that we are typically in the cyber physical systems, we are seeing distribution or distributed systems, right? So network heterogeneity is one thing that we usually see. This means that we have IoTs, we have cloud, we have gateways, so on and so forth, different systems with different capabilities, right? So that's one key thing that we need to pay attention to. Another is the notion of sharing. So more and more these days, we see that devices are becoming more and more share friendly, which means that they want to share either their data or in recent, for example, if you have heard about Amazon Sidewalk, essentially the idea is that you can even share your bandwidth with your neighbor. The idea is that, if you have some capabilities and you're not using it, you can amortize the cost, or you can improve the performance or improve the service by adding this sharing capabilities. And while this sharing is interesting and gives us lots of new opportunities, at the same time, sharing becomes a security important issue, right? For example, if I'm using the bandwidth of my neighbor, if I'm an adversary and if I want to use this maliciously, what can I do, right? So these are the things that we need to think about. Another important thing is the new and different standards and protocols that's coming to the standard systems. LoRa, 5G, new technologies for communication, and so on and so forth. These are things that kind of differentiate the realms of cyber physical system security to what we had previously in network security, such as TLS and Wi-Fi and so on, right? And then there's a whole bunch of things such as wireless sensing and wireless systems. So location, time, the type of material. So these are usually the use cases of the wireless sensing. But in all these cases, the privacy and security is an issue. So for example, if you are able to use wireless sensing for sensing the location of people, let's say in a room, while this is also very interesting, at the same time, what we are experiencing is saying that basically the privacy of these people in the same room will be violated. So there will be lots of privacy concerns in this systems, right? So lots of opportunities, there are lots of things that can be done with wireless sensing, but at the same time, there are privacy concerns comes with it. All right. Any questions on the networking side before we move on? Cool. So on the cloud side, there's not much to discuss. We already extensively discussed the side channel, privacy, integrity, trusted execution environments, and all those things that we discussed basically goes into here, right? So I'm not going to take much more time discussing this. Basically, all we had discussed, especially on the hardware security, trusted execution, and so on. This is exactly the application is here. One major thing to think about is that, of course, there is interest in moving away from centralized cloud computing to decentralized systems such as blockchains. So that's also another interesting area of research, especially for security, where we kind of altogether get rid of centralized systems, and now we have a blockchain systems that we can do things. And with blockchains, we can actually address some of these problems, not all of it, but then of course new problems will come into light, right? So that's also, we wanted to talk about blockchains a little bit in this course. We didn't have time during the the part that we talked about crypto. Maybe in future offerings we talk a little bit more about blockchains. But I'm sure most of you already have heard about blockchains, or if you're interested, I think now you have the cryptography background to understand what is a blockchain. So you know what, for example, hashing is, you know what digital signature is. So you probably should be able to mostly understand how blockchain works. Any other question from the cloud part? Okay. So then once we have the cloud part, of course, there is a connection back between the cloud, and there's this notion of edge and cloud. This is basically what the goal of this course was about. So, I mean, the title, of course, is, you know, security in edge, right? So, I mean, generally what we should do. So there is all sort of, you know, implementation issues that is not relevant to the security, but generally when we are talking about, you know, security part, there's difference between the local one, the cloud one, and local cloud one, right? So if you have an edge, we have cloud. If the processing happens in each one of them, we already talked about the threat models. Distributed systems that I just described could potentially bring out another area of research and another source of, you know, issues with security. And we also talked extensively about air gap systems, which is kind of also in this realms of, you know, edge and cloud systems. So systems that are, for example, have their own internal network. So many, for example, industries, instead of like having individual devices connecting to the open internet, they usually have an internal connection between them. And then this connection is usually has this gateway here, and this gateway is actually connected to the open internet. The difference is that people outside, the adversaries that are on the open internet, can only attack this system here, but they cannot attack these individual devices via network. And this way, we can basically create a very strong defense mechanism here, and making sure that the system is capable of defending itself, right? So these air gap systems can help us significantly with, you know, reducing the number of attacks. But of course, we talked about various ways of attacking air gap systems as well. So it's not like, you know, oh, okay, so as long as we are making this connection, you know, restricted to the outside world, we are good to go. We actually, unfortunately, things like physical side channels can break this assumption, right? And one more thing that I want to show is that I kind of described this when I was talking about side channels, but the trend is, you know, we are more and more seeing more edge devices and more capabilities. So cyber physical systems, as I said, is on the rise, are in the rise in an exponential manner, actually. So we're going to see more and more. So the security of this also becomes more of an issue. All right. So the last part of the puzzle is the actuation. Again, the same old confidentiality, integrity, and availability is the main thing. The actuation is actually where, as I said before, is where the attacks gets meaningful. So we always want to attack either the sensor or the local or the network or the cloud until we actually have some meaningful actuation. And the adversaries are really interested in doing more powerful stuff here, right? So this is what we need to be worried about generally when we are using more and more cyber physical systems. What should we do? What are the defense mechanisms? So there are various ways of defending against this. Hardware support is one of the key ways of making sure that the actuation is protected. So for example, if there's a command that's doing something that we're not expecting, maybe hardware support can stop that and fix that. So generally, hardware approaches is one of the key ways of protecting actuation. There's this notion of what's called a proof of work. What the proof of work is basically saying is that the actuation gives this assurance that the command that has received is the same command that the sender has received, and also gives this assurance that this command has fully executed and the results has been reached and sent back. So proof of work is basically just giving you this three things that we are kind of care about. And there are also lots of research on how we provide this proof of work, what are the minimal things that we need to add to the system to provide this proof of work, and so on and so forth. Another interesting area of research is, sensing and actuation pair. So for example, in order to validate the sensor, we can use actuation, send some signals and receive it. In order to validate the actuator, we can use the sensor to receive some signals. So there is lots of innovative things that can happen between the sensor and the actuator in order to verify each other. So one of them has to be trusted and the other one needs to be verified. All right. And as I said, the actuation is where the main applications come in, right? So for example, think about medical actuation, right? So like, an implantable device that is implanted on someone's body. If we manage to attack that, then the actuation would be something that's like, stop working, like, uh, 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 stop the process of that device, stops the normal process of that device. Of course, the impact would be detrimental, right? So the application and the impact of the actuation could be huge depending on that sort of application. All right, so kind of, as I said, this is more of like, just an exploratory lecture. Just wanted to give you what is out there because most of these things we kind of discussed. And the others, if you want to go into the details, we don't really have time, but just wanted to give you a big picture of the things that we have discussed so far, right? There are lots of examples of real attacks at different parts, the sensing, the processing, the network, the cloud, and the actuator, specifically at these 3 levels, and actually the network layers levels as well. And then on Wednesday, we're going to see some of these papers. If you're more interested, you can actually go through them and read some of them. We kind of go through the differences and similarities. The main thing to understand is that the interaction with the physical world is what's distinguished cyber physical system security than normal cloud or computer-based security. This has more opportunity for the attackers, unfortunately, because the attacker can interact with the system maybe better, so can launch the attacker more easily. And the impact of the attacks could be more significant as well, because that could create physical attacks in the systems. But generally, this is very, very growing area of research, many different applications, different sensing modalities, heterogeneity, and so on and so forth. And the biggest thing to remember is that, cyber physical systems is kind of coupled with constraint. We have constraint in terms of energy, we have constraint in terms of communication and so on, because the form factor is small, the cost has to be small, the energy consumption has to be small, right? So there are lots of constraint, and this constraint also translates in any sort of defense that we want to propose, right? So for example, on our server, we can have large, systems such as trusted execution environments. We can have large overhead, defense mechanisms. But on something like cyber physical systems, any sort of defense mechanism has to be very, very minimal. All right. So keep in mind that this is also important. All right. So that's the end of the lecture for cyber physical systems. Let's have a quick, 2-3 minute break. I'm going to come back, and if you have any questions about this, I'm going to answer, and then I'm going to continue talking about hardware security as the next thing that we want to talk about. All right. So let's come back maybe at 3:02. All right. See you guys. All right. So let's just come back and talk about the next topic in today's lecture. Any questions before we move on? So hopefully when on Wednesday we talked about these things, when people start, presenting some papers, you get a little bit more idea of the different flavors and different types of attacks that can happen at various different points of a cyber physical system. But again, if you are more interested in any of those, areas, I suggest you to go and read more about them and read more papers. You can start with finding the relevant papers in the paper list, and then you can maybe follow up with the works that are relevant to those works and so on and so forth. But I'm sure you already, found those papers in various ways. Okay, so now let's talk about hardware security, which is kind of in some aspects are relevant to to what just we discussed in cyber physical systems. So let me start sharing again. All right. So so logistics, we already, any more questions about project finals, anything? Okay. So we want to talk about hardware security, and when we were saying hardware security, of course, the first question is what do we mean by hardware security? Are these all these things that we kind of discussed is hardware security or not? There is a simple answer for what hardware security is. It's mainly attacks and defenses that are purely in hardware. Well, what we mainly mean by that is, when we were talking about the vulnerability or the protection of that vulnerability that is solely coming from the physical device rather than the software, all right? So we're kind of like, talking about things that purely caused by the hardware or being purely defected by the hardware. These are mainly, what we say of hardware security. Of course, there's computer architecture security as well, which you may argue that this is a hardware security or this is a computer architecture security. That depends on who you talk to. But the architecture is slightly higher level than hardware itself. So when we were saying hardware, we were talking about gates and circuits mainly. All right. So for example, physical side channels is kind of like, an example of hardware security. We already talked about physical side channels, but we want to talk about other things that happen in hardware security. So two things that we're kind of going to talk about. Probably the first part would be this lecture and the second part would be second lecture. The first part, we're going to talk about two main components in hardware that is relevant to increasing the security of the systems, mainly what's called PUFs, or some people call it PUFs, and also TRNGs, or true random number generators. All right, so these are the main two things. And the use case of these two are mainly for creating and storing secure keys. We already talked about why we need keys and how the crypto algorithm works, and how from a crypto algorithms we can do messaging and securing systems and so on and so forth, through networking, through trusted execution environment, so on and so forth. But we didn't really talk about how we really implement this in hardware. How do we store keys? How to make sure that keys cannot be, inferred, and how the adversary cannot attach, use this and find this and so on. So we're going to focus on this part right now. So as I said, we started from the top and then go to really, really bottoms of circuits and gates of the systems. The second thing that we going to talk about is the issue of supply chain security. And by supply chain, we mean the silicon supply chain, the supply chain for building chips and building computers. And we mainly going to talk about hardware Trojans, and one of the key things in supply chain security. We're also going to talk about different attacks and defenses and IP protection and all various things that can attacks in supply chain, all right? And this is actually, supply chain is becoming more and more important these days, and I'm going to talk about why and how it becomes more important, all right? So this is kind of the agenda for the hardware security probably. So we're going to just, talk, I'm going to talk for another 40-ish minutes. If we can finish it, that's great. If not, we're going to continue the rest of it on Wednesday. All right, so let's talk about the first part, which is PUFs and true random number generator. In order to understand why we need them, we need to kind of go back a few weeks back when we talked about trusted platform modules, or TPMs. Recall that we said that essentially in order to trust computers, we have to start the trust from somewhere. And that somewhere, which we call it, TPM, which was, the hardware manufacturer puts set of, keys and some functionalities, including, hash functions and attestation and so on, and package it into one piece of silicons and use it and put it in our motherboards. And we kind of build a trust off of that. We already discussed how we can do it. Well, that's where, the whole stories of our secure computer systems begin. What we didn't discuss was, okay, how do we store this digital information, for example, the keys, the secret keys, in a way that is resistant to physical tampering and physical attacks? How we make sure that when we are, storing these values into our TPM, somebody cannot maybe just simply run a side channel attack or any sort of, even memory attacks in order to read this, right? So that's the key, the very important part when we are building this hardware, right? So we want to talk about that and think about the possible attacks. Two things that are obvious. One is while the data is being read from the TPM, someone can probe into the circuit. So for example, if this would be TPM and this would be your pins, somebody can basically literally probe this using, for example, an oscilloscope and reads the voltage and knowing that whether this was 0 or 1. So this is usually what's called physical tampering. And then another thing that can be possible is if this values are kind of available even when the computer is off, then maybe, well, I mean, the adversary can read things off of the values that's stored in the SRAM or on the systems, sending some pulses and receiving some responses and so on and so forth, right? There are various attacks in the literature to talking about these things if you're interested to know physical attacks on TPM. But generally the idea is that we want to make sure that the key, both during the storage and during the usage cannot be easily read by a physical attack, by a physical adversary. Right. So in order to fix this issue, one of the interesting solutions is that instead of actually storing it and then have this whole problem of, okay, let's store it and then let's move it and so on. What we can do is that we can have a mechanism to generate keys dynamically, right? So the idea kind of seems simple. Basically, all we need to do is that having a function that's kind of like, by some trigger, just generate the secret key for us, right? And if we have that, and if it's securely create that, and if the secret key is the secret key that we are expecting, then kind of like, it fixes all those problems that we have, because then we don't need to expose this to a motherboard. When the system is off, this function is off as well, so we don't need to worry about storing anything in the system, right? So how do we do it? And this is basically done with what's called physical unclonable function, or PUF. The idea of the PUF is that it is an actual physical, structure. Think about it as like a multiplier or adder or something like that. That as input gets usually a challenge. This challenge could be a simple 0 or 1, or it could be an actual value, or it could be even an analog signal. And based off the channel, it creates a response, which that response is basically the secret key that we want, right? It could generate multiple different responses, multiple different keys. We're going to talk about why we might need multiple different keys. But in most cases, it just generates one single response, which is the actual secret key. And the idea is that we can secure this into a secure on our, like maybe TPM. And then in that case, instead of actually storing this key physically into the memory of the TPM, we need to store this PUF. And why would be this important? Because by tampering PUF, the attacker cannot get the secret key. The attacker can only get the secret key if it sends the right challenge, and then if it's able to actually probe this part. And we can basically engineer the hardware to make sure that this part is not exposed to the outside board. So this option is kind of removed. And in that case, we are kind of removing the chance of this secret key being read outside this system. All right, so that's the main idea and main use case of a PUF. Any question at this point? Okay. All right, so how do we build a PUF? In order to understand how we build it, we should first understand what is the threat model. So the threat model, or let's call it differently this time and say what is the desired model, is that we want a function that has two capabilities. Number one capability is that it has to be easy to measure, right? Why? Because think about this, that we need this secret key and we need this for every single communication that we have, right? So if it takes a lot of time to generate that secret key, then it wouldn't be an effective solution, because every time that we want to generate a secret key, we have to wait for a long time. So we should be able to easily measure this. And by measure, we mean this part, the creation of the challenge, the response, right? So it should be easy to measure. On the other hand, when we're seeing a specific PUF, it should be hard to predict what that outcome is. So think about this as a random function when we talked about, cryptography algorithm. We not be able to easily predict when we're seeing this input, what would be the output. And then if the output looks equally to a random distribution, that's when we get the maximum security possible, right? So for PUF, this is what kind of activity and behavior that we are expecting, right? And then as I said already, this is kind of like, more elaboration on the hard to predict part, that we want to, the output looks random for any given input. So basically by even sending multiple inputs and outputs, the adversary may not be able to detect what the actual functionality is, right? So this is kind of like, the desired functionality of a PUF. And then if you reverse it, that would be our threat model as well. So the threat model is that the PUF is the attacker can basically physically explore the PUF and being able to measure things, or the adversary can see the output of the PUF and check it with some specific pattern and so on, right? Okay, so now let's go back to how to build a PUF. So we know why we need a PUF. We need what sort of behavior the PUF should have. But now let's see if we actually can we build a real PUF, a feasible PUF in a system. And the very interesting idea, very innovative idea of the PUF is kind of like connecting the physical characteristics of silicon, a piece of chip or piece of silicon, into this idea of challenge response paradigm. So basically the key idea is that every single chip, every single die, every single device that we create has unique physical characteristics. And if you go deeper, we can see that there are three main things about this uniqueness. The number one is that replicating two similar devices is very difficult. So we typically call this process variation when we are thinking about circuit design. So if you want to create two devices that has the same behavior in process variation, it's almost impossible to do that. The second interesting thing is that, for example, measuring this unique physical characteristics, be it variation in temperature or variation in potential and so on and so forth, is very trivial. It's as easy as having a sensor for measuring temperature. And then finally, predicting them is basically not better than any brute force algorithms. Why? Because for a given chip, there is multiple different ways of process variations. You have to do multiple simulations and all those things, right? So it's not that you can predict that, if I build this device under this condition, this would be the response to the process variation. It looks completely random and could be any values that we can have in this space state domain. So it's kind of like has all the capabilities that we want. Look at the physical characteristics of the system, use that to kind of like create a challenge. Sorry, use that to create a response for a given challenge, and use that as your secret key, and then move on with that. So basically that becomes your secret key. Use that in your crypto algorithm, so on and so forth. You already know the rest of the story, right? So what we do is we build multiple different devices. We actually think about, okay, how do we leverage this process variation as much as we want, as much as possible? And then we create this, and then we maybe measure it. And now this way we know that for this specific challenge, this is the specific response that we get. And this is the, the random, the secret key that we're gonna have. So for example, the manufacturer, once it's manufactured, it can actually store these pairs, know that what the secret key for this specific device is, then ship the device, and nobody else can actually never know what this exact, what this response for this value is, right? Let me give you an example, maybe that helps you a little bit better. So basically, usually the key idea of PUF is one of the most popular ones is what's called a silicon PUF. And the idea here is that, for example, because of the process variations, the delays of circuits, even if they are exactly equal to each other, so assuming that this is a combinational logic and this is the exact same replica of the same combinational logic, since these two, because of the process variation, even though they are on the same chip, they are at different physical locations, the delays, excuse me, the propagation delay of this one and this one, give me a second. Okay, so the propagation delay of this one and this one and this one is not the same. And because of that, if we are sending a pulse here, the time that it takes to receive the pulse here versus the time that we take to receive the pulse here might be different. And the interesting thing is, for every single chip that we design, this difference between the timing of this and this are completely different than the other, and it's completely random, okay? So if we, for example, say, if it reached to this point, this is 0. Soon, if it reached to this point sooner, this is 0. And if it's reached to this point, it's 1. Sooner, it's 1. Excuse me. And then we can replicate this as much as we can. Then what happens is basically this. Excuse me. Let's have a 30-second break. Okay, continuing. So we are sending this pulse, and we are measuring when this pulse arrives at this point, and this point. And for example, if it arrives at this point, we call it 0 first. And if it arrives first at this point, we call it 1. And then if we want to have multiple bits, we can just replicate this. And then what would happen is that when we are building this circuit here, many times, because of the process variation, this distribution and which one goes first and which one arrives second is going to be completely random and different. And this way, this would be basically the idea of creating a silicon PUF. So for example, what I'm showing here is a multiplexer. So this combinational logic that I was showing here, in this case, is a multiplexer. There are ways that we can, put this multiplexer and putting at different points. Then at the end of the day, the data would be here. So as you can see, we are sending a pulse at different directions. And either this pulse arrives at this point before the positive edge of the clock, or this pulse doesn't reach to this point, so this value would be equal to 0. So if the pulse reaches, the value would be 1. If the pulse doesn't reach, the value would be 0. So the why, the secret value that we kind of want to use really depends on delays of these individual muxes. And as I said, if you build multiple of this, the delay of these individual muxes would be completely different than the other. So the value that we get here is completely kind of random in terms of distribution. All right. And what we can do is that we can measure this one time. And that's where we actually create this challenge and response paradigm. And then, by the way, look at this is basically when we are setting the challenges, you basically can pick whether we are taking this path or whether we are taking this path, right? So the challenge is basically, in this specific example, is a set of zeros and ones as the selector of this multiplexer. And basically by changing this challenge, we can pick any of permutation of these multiplexers. So what happens is basically for a given set of challenge, we can measure this during the hardware manufacturing phase and record this value here. We run this multiple times for all these different circuits that we have, and then we're going to have a series of zeros and ones, whatever, right? Let's say it's an 8-bit or 64 bits, or depending on what sort of secret key size we want to have. And that would be basically the secret key for this specific circuit. And as I said, people have shown that if you build similar circuit, even in the same design, same node, same company, so on and so forth, this string of value would be different for each of them. So it would be a unique ID in some sense for each of these circuits. And that would be what we call the secret value or secret key of the system. So this can be actually used as the secret key. All right, so that's the idea of a silicon PUF. Any questions at this point? So in other words, and I'm like putting some notes here, we are kind of translating the process variation into numbers, and that would be where we're gonna get our secret key. And since process variation is a random process and is different and unique for each device, then we can rely it as source of secret, and then we can build cryptography algorithms. All right, so that's the whole idea of silicon PUF. So somebody have a question? No. So what is the security of the PUFs, PUFs? So it really depends on the application. So we usually use PUFs for two things. One is for key derivation or generation, and the other for authentication. And then we're going to talk about each of these and see what is the difference between them and what sort of security we require. So for key generation, for secret key generation, we typically need only one pair or a small pair of challenge response pairs, right? Because essentially we want to have one secret key and use it, or multiple secret key, but the numbers would be very small, right? And so we usually call this what's called a weak PUF. The requirements here is that it has to be very, very hard to predict, because that's the only value that we're going to use as a secret value. It has to be resistant to invasive attacks, right? Because since we are only sending a few challenges and we only get specific response, we don't want that response to be known. So that response has to be held secret and has to be protected. So the design of the system should be such that you cannot probe it easily as an attacker. So everything has to be internal. If the attacker wants to probe it, it has to destroy the system. So it's essentially that's the way we're gonna make sure that it's secure. All right. So the weak PUF is usually used for key generation. And the only thing that we need to have is a circuit that creates a unique response to a specific challenge. And that challenge and that response should be unique for different devices and should look random. If we have that, we have our weak PUF, we can use it for secret key generations, and then use it, for example, for things like AES or RSA and so on and so forth to create our encryption and decryption crypto systems. All right. So to just give you another idea of like what other things that we can do is that, for example, instead of like silicon PUFs, we can have like an SRAM based PUF. For example, people have shown that the power on state of an SRAM is something that is completely random and actually can be used, and is also process variation dependent. So you can actually use that in order to create your response. And it only has one challenge, right? It's only on and off. So it's not like, you can have multiple challenge and response, but that one single response could be good enough for your secret key generation because it looks random, hard to predict, hard to measure, different from different devices, and all those things that we are looking at. The second class of PUFs are used for authentication. And here, here we don't only rely on one challenge response pair, but we also need to have a large set of challenge response pair. Why? Because if you want to authenticate the device multiple times, we should be able to send multiple challenges and receive multiple responses. If for every single challenge we send, we get one response, then the next time an attacker can mimic this behavior and send us the same response, right? So there should be a large list of possible challenge and response, where each time they use one, we no longer use this one, we can move to the next one and next one and next one, right? So the idea is that for authentication, we need a large set of pairs. Otherwise, if we use one pair, we cannot reuse that pair anymore. And then if you don't have enough number of these pairs, then at some point we can no longer authenticate the device, right? Again, the challenge response should be hard to predict. So assuming that the attacker sees a finite number of challenge and response pairs, should not be able to detect a new challenge and response. But the difference is that the response is also available to the attacker. Unlike the previous scenario where we are saying that the response has to be kept secret, at this point, we are saying that the response can be seen by the attacker as well, but the idea is that there should be lots of challenge and response variables. So in this case, and then we call this a strong PUF compared to what we call the weak PUF. Just make sure that, by saying weak or strong doesn't mean that in terms of security they're weak or strong. This is just a notation that we typically use, all right? So, back to examples that we had before. For example, things like power on SRAM cannot create a strong PUF. Why? Because it's only one set of, challenge and responses. But maybe something like, this silicon MUX-based PUF, if we have enough line of delays, we can have a large set of challenge and responses, because this would be basically 2 to the power of how many of these lanes that we have. That would be a number of challenges that we're going to get, and the responses would be also equivalent to that. So something like this would be a good candidate for a strong PUF. Something like power on SRAM could be a good candidate for a weak PUF, right? And one interesting thing that these days are happening is basically using machine learning to kind of predict the model of the strong PUF. So these days, another requirement is that not only it has to be hard to predict, but it has to be robust against machine learning as well. So these days you will see ML-based or ML-robust PUF. It's kind of like trying to make sure that, if you're using a replica and trying to build a model based off that and trying to predict the next challenge and response, the PUF is still doing some unknown activity. So the machine learning accuracy model would be pretty low, all right? So one last thing that I want to discuss before moving on to the next concept is the challenges with the PUF. And the main challenge with the PUF is dealing with the noise, right? The problem is that there are sources of variation during the execution of the systems, during the implementation of the system. And that could create lots of problems, because remember we said that, for example, we have 2, path, we send a pulse here, right? And we are basically measuring which one arrives first, right? This one or this one. And we said that because of the process variation, this is kind of unique. The problem though is that other source of other source of variation, including temperature, can also impact this delay and this delay. So dynamically, this value can change because of things that are not relevant to the process variation, but to the temperature variation, right? So what we want to have is a system that's only responsive to the process variation, but is robust against other sorts of noises, all right? So that's what we kind of want to deal with in in a PUF system. So what are the typical solutions? The typical solutions usually either error corrections. So typically what we do is that we know that, for example, temperature can change things. So there are some error correction systems that can actually fix those non-process variation related changes. Another trick is usually using differential dependency. So if you, for example, we have two paths to the system, while the process variation can impact this differently, so it might be this one might be slower and this one might be faster. When we are talking about environmental variation, such as temperature, if the temperature goes up, the delays for this one and this one goes up at the same ratio, all right? So if you're looking at the difference between these two, the difference is only impacted by process variation and not by the environmental variation, because whatever impact the environment has to the system kind of cancel out each other when we do the differentiation, right? So that's typically the trick that is being used when we want to make sure that the system is only responsive to the variation caused by the process and not the other variations that are in the environment. And this is what we do. All right. Any question at this point? All right, so what are the research questions for PUFs? One thing to note that is, PUFs are a pretty established area of research already. This has been proposed, I think, around 2007, 2006. And during 2010s era, decades, there has been lots of works on different PUFs. So these days you will see less and less number of papers in this area, but still there are some interesting works. The main unsolved challenges still are low overhead, because essentially PUFs is a circuit for itself, so it has some overhead to the system. So having strong security without actually having large overhead is still an area of research. A fast response, a strong PUF. Again, these are interesting things that people are still looking at. And looking at the new technologies, such as new integration technology, new types of PUFs, for example, putting it into the memory or using, as I said, SRAM. New types of innovative PUFs are something that's being done these days, and it's an area of research that people are doing. Okay, so I'm going to pause here. Is there any questions? Okay. So what we're going to do is that we're going to talk about random number generators and supply chain security on the next lecture. We're also going to go through the paper presentation next lecture as well. And that's kind of like going to conclude most of the things that we want to discuss in this course. Next week, if you have time, I need to review all of the things that we discussed in the course. We probably just very briefly going to talk about malwares and different types of malwares as well. All right. So that's it for today. If there's any no more questions, see you guys on Wednesday. Probably Wednesday will be in person, but let's see what happens.